Welcome back, everyone. So as I was just saying, we're about to finish chapter 23, which is our last traditional organic chemistry chapter. After that, we have some chapters on biochemistry. On Friday, we'll finally close the loop with spectroscopy. And I think this cat wants to be on YouTube. Say hi, YouTube, Bella. Anyways, where was I? Right, so we'll finish on spectroscopy, and then we'll have some biochem chapters. I believe we'll have carbohydrates, which is the one I'm going to have the most to say about. I like doing the biochem chapters. I kind of do them in order of the ones I have, the type of molecules I have the least to say about to the one I have the most to say about, because there's quite a few interesting and relevant structural issues with carbohydrates. And then kind of our capstone chapter on both semesters is going to be 29, which is on metabolism, in which I will try my best to convince you that all of these reactions that you'll have learned some about in biology classes, that you'll go on to learn about in biochem, are nothing other than applications of things we've learned these 2 semesters. They literally are the same reactions. They're just dressed up in different clothing. And after that, our last day of class will be for the engineering majors and the material science majors, because it will be on polymers. So you'll have been very patient through both semesters, and I think we've covered other things relevant to those fields. But in any case, that last day is all for you, because and also, even if you're going into medicine, it's not like you won't ever be using anything made of polymers. Heck, we're all using polymers right now, sitting on, using, wearing to some degree. So anyway, and I think that will be it. I don't think I've forgotten anything. Please do register your attendance. I don't have Reef pull-in questions today. I might not have, I can't seem to find anything before proton NMR spectroscopy, but be that as it may, please do register your attendance. We want to make sure you get credit for that. Last time we ended on the Claisen condensation, and we went over the mechanism of this admittedly relatively boring reaction, just involving the condensation of 2 molecules of ethyl acetate to make ethyl acetoacetate. And we went over that mechanism. We pointed out how there's no dehydration because it's a moot point. At the point where we get that oxyanion, the oxygen with the minus charge, and start thinking about doing some proton transfers and some dehydration, it's a moot point because the carbon-bearing O- has an alkoxy leaving group on it, which is normally not a really great leaving group, but in alkaline solution, ouch, she weighs a lot. In alkaline solution, it's good enough. And so we covered that last time. I also want to make you aware that mixed Claisen reactions and intramolecular Claisen condensations are also a thing. And we had quite a bit, I am estimating that I'll have a little bit of extra time compared to the previous class, since a lot of our structures are already drawn. Indeed, a bunch are already in the class notes. So I have an example of an intramolecular Claisen condensation in your class notes. What I do not have is an example of a mixed Claisen condensation. So let's do one. I haven't even worked out what the product's going to be. Isn't it exciting? But I'm mixing 2 esters, and I've here specifically picked one that has no alpha protons. So this one cannot be deprotonated. Oh, I've got an even better example. Let's not put a tert-butyl group, since one could argue that might make it too bulky. Let's not put a tert-butyl group there. Let's put a benzene ring. Because, whoops, that's no good, is it? Because that will also have no alpha protons. Perfect. I wish I'd thought of that beforehand. So we'll treat that with ethyl benzoate. Right, because that carbon is also quaternary. There's no protons attached to the alpha carbon. So ethyl benzoate cannot be, cannot form an enolate. It's non-enolizable, as we call it. So we'll treat it with that. And not only that, I've really put my thumb on the scale, so to speak, by picking as the other partner diethyl malonate, which has two particularly acidic protons. So I can kind of get a picture of what we're going to get, at least vaguely. Probably you can too, but let's figure it out. But I have little doubt that this reaction would work and would cleanly produce just one Claisen product. So we're going to first react it with the base, with our sodium ethoxide and ethanol. Again, you'll notice I'm being careful to make sure my esters and my base and my solvent all match. I want to make sure that we don't scramble the esters. And again, I want to make this point. It's not that what we're doing is preventing ethoxide from attacking any of these ester carbonyls. We are not preventing that. That will most certainly happen and happen a lot. It's just that there's now no consequence, because once ethoxide attacks one of those carbonyl carbons, the only thing that can happen is one of those two identical ethoxide groups will come back off. And so there's no chemistry, there's no chemical consequences or reactive consequences of that. So, oh, those are not methyls, those are hydrogens. So we'll start by treating this mixture of esters with our base, and then later on we will very carefully acidify. And another thing I want to be sure I clarify is how and why we need to be so careful about acidifying reactions of this type, especially Claisen, since they involve esters. We can be a little bit less careful. I still wouldn't go using a blowtorch. We can be a little bit less careful with aldol condensations because they involve ketones and aldehydes. But the first step is going to be, actually, let me write out also one of these ester groups, since I like putting the minus charge on oxygen when I make an enolate. If you'd rather put it on the carbon, go right ahead. It's absolutely acceptable. Of course, assuming that your mechanism is otherwise correct, right? And assuming there's no carbons with 5 bonds, all that stuff. Good, so now I think we're finally ready. So first step is going to be deprotonation and forming the enolate. And there we go. So that's going to be the first step. And so this will give our enolate of diethyl malonate. We learned about that compound in the chapter on the acetoacetic and malonic ester syntheses. I erased that proton. It's of course still there, the one on this sp2, now sp2 hybridized carbon. And we have O- here. Let me also, I like putting on electron pairs, at least on atoms that don't have a formal charge of 0. I think it just clarifies that. Good, so there's our enolate, and now this can go ahead and attack our ethyl benzoate, which I'll put over here. I'm just going to put pH for the benzene ring. Of course, you don't have to if you want to draw up the benzene ring with either the bonds or a circle in the ring. Or maybe you like to write C6H5. Go for it. Completely acceptable. Those are our personal preference things. You are the boss of your sauce. I'm trying to think, what would Chef John say using structure? I can't think of a word that rhymes with structure or a name. Oh, you know what? I did it again. Dang it. I did this in the last class too. That mistake you see is one that I often make, and students don't usually, but I often make that mistake. I think it's because I'm working too fast. Of course, it's not the oxygen that's attacks, but the carbon atom. So we're going to form a bond between that carbon and that carbon. And that's what I'm trying to show with my arrows. I would be able to make those arrows a little shapelier and better looking if I were using chalk on a chalkboard, but that's what I'm trying to show here. I think this shows that adequately. I'd be able to do it better with a pencil and paper or chalk on a chalkboard, but that's acceptable, I think. I can live with that. And so we're going to get now we've reformed this carbonyl. This ester group will still be here. This is the new, of course, those ester groups are the same. I've just drawn one of them out because I think I actually am going to need it in a little while. Let's see now. So this used to be the carbonyl carbon. So we're going to have yes, we're going to have let's see, we're going to have phenyl, ethoxy. Actually, maybe I'll make this O minus. I'll put OH for now, and I'll put the minus on it, and ethoxy over here. Then when I put the minus on, that H will go away. And finally, let me move it out of the way of that arrow. Good, so that should be the intermediate that you get. And as we said last time, this is where, if this were an aldol condensation and we did not have an alkoxy group attached to that carbon, we would look to be protonating that oxygen using the solvent. But that's now not going to happen because we've got a good enough leaving group over here. Again, normally hydroxide and alkoxide are not such great leaving groups, but in alkaline solution, they're good enough. Acidic to neutral to acidic solution, no way. But alkaline solution, you're fine. And so I think your next structure will look like that. And you say, well, we're done because that's my final product, right? Yes and no. It is your final product, but we are not done. Because we have here an extra acidic proton. And you could, there's probably a way to set up a reaction like this so that there are no acidic protons left after the, there are no protons next to any carbonyls anywhere in the molecule once you've done your first addition. That would take some effort. It probably can be done. But again, remember, we're still in base, and there's no way we can prevent that hydrogen, that proton from being pulled off. So get pulled off, it will. I'm gonna shoplift this ethoxide from up here. Well, I'll make a different arrow. Pixels are cheap. And you could also, this enolate actually is 3 different resonance forms, right? Although, actually 4. You could put the minus charge in carbon, or you can put it on either of those 2 equivalent ester carbonyl oxygens, or you can even push it through to the ketone carbonyl oxygen, whichever you like. You are the Alexander the Great of your enolate. And so it's actually this enolate, in whichever resonance form you want to draw it, that's going to be the exclusive species while we're still in alkaline solution. And this extremely well stabilized anion will be swimming around happily, taking in the scenery, until we add acid, dilute aqueous acid. And we need to do this very carefully. I noticed in my class notes here, I was pretty careful to write dilute at H3O+. Because it's best practice both to mention that and, of course, to do it. You might be thinking about, I don't want to give the game away, even though I think I said it last time. You might want to be thinking about why this is indeed best practice to use dilute acid, added very carefully, probably keeping it nice and cold. This is the time for subtlety. But once we do add that, of course, we'll reprotonate that enolate. And here's another opportunity for me to make that mistake. I know why students don't make this mistake, because they listened very carefully when their professor said that enols are more stable than the keto form. So we're going to form a bond between this carbon and that proton. And again, just to clarify, it's this carbon that we're protonating. And then we will isolate the ketodiester. Looking like that. And of course, you can draw the proton in if you want to, but it's understood. So that would be the final product in this case. I don't see any stereochemical issues. There's no alkenes. In fact, not only that, that carbon isn't even chiral, right? It's got two ethyl ester groups on it. So this is very boring in terms of stereochemistry. There's no stereochemical issues, so we're completely fine showing it that way. Good, so that's an example of a mixed Claisen condensation. Again, we've carefully picked our reacting partners so that only one product is possible. We picked one of them that has no alpha protons, so it cannot be deprotonated. And just to be on the safe side, we even picked the other one that is extra acidic protons. So there's no way except that this one will be the donor and this one will be the acceptor. We'll make the enolate here and it will add to that. So I didn't get a chance to go through an example like that with the previous class. Can you explain why it's important for the H3O+ to be dilute? Well, I kind of wanted you guys to think about that a little more, but that's okay, we can get there. You'll notice, and there's often more than one reason, you'll notice that in this case, we've got ester functional groups. So who remembers what happens when you treat an ester with strong acid and you heat it? That would be chapter 21. Hopefully you're thinking in terms of hydrolysis. And actually, this would even go further. This particular one, you would hydrolyze both esters, first one, then the other, and then it would decarboxylate. So that's a chapter 22 thing, because we've got a derivative of a malonate ester over here. So these are the things you have to be thinking about. You have to be thinking about the structures that you draw and analyzing them. So you would want to be very careful on adding acid. I would even be afraid to use something like sulfuric acid or HCl. If it were me, I might do like, I don't know, aqueous ammonium chloride or something like that. I would want to be very careful just to make sure that I don't hydrolyze either of my esters. But if you are, then I think you'll be able to isolate this ketodiester. And we'll talk more about examples of what the acid will do. That's a point I'm going to make several times today. Good. So any other questions on this? And again, this in its whole will appear on YouTube. So you'll be able to see all of this. There's no need to scroll and wait or scroll and wait. You'll be able to see all of it. Make sense? And it's a good question about the acid. We'll talk about that more. We'll have more examples where that pops up. So another possibility, this one happens to be already in your class notes, is being able to have an intramolecular Claisen condensation, just like you could have intramolecular aldol reactions. This particular one starts with a symmetrical diester, so I think there's only one product. What if it were not symmetrical? Well, again, remember, in mechanism problems, the tendency is to give you the product that you want to aim for. So you'll know by looking at the product which way to proceed with the reaction. But this one here, I've numbered the carbons. As I think I said the last time, students, especially students who say they are visual learners, have told me they find that helpful. I am not a visual learner, I am a verbal learner, but I still find it helpful. I want to make sure I don't screw up. And I think here you'll find that we'll get a 6-membered ring. So look for the possibility of forming 5 or 6-membered rings, as opposed to 3 or 4 or 7. But 5 and 6-membered rings are especially favorable to form because they go through a very low energy transition state. But the reaction starts just like the others. You'll notice again, I'm matching the base and the solvent to the ester. These are methyl esters. So I'm using methoxide base and methanol as the solvent. So you always want to make sure you match those so that you don't scramble the esters. For the same reason you wouldn't want to use OH minus, hydroxide as the base. If you did, then you would saponify the esters and you'd wind up with carboxylate groups, CO2 minus. So in order to make sure nothing unseemly like that happens, we'll make sure everything matches. And you'll pull off any one of these 4 protons, they're all the same. So you'll form your enolate. Of course, there's 2 good ways to draw the enolate. I don't care what you do. And then if you number your carbons, you'll see that you're going to form a 6-membered ring. So, right, resonance stabilized species. And then this blue bond here is the one we just formed. So you can see we've made a 6-membered ring. Here's the point where we lose our alkoxide leaving group. That's not possible in an aldol condensation, but it is in a Claisen condensation. And again, even though methoxide is not a particularly good leaving group, in alkaline solution, it's good enough. You would never lose an alkoxide or hydroxide leaving group in neutral or acidic solution. But in alkaline solution, you're good to go. Then you can surely rationalize it. The pKa's are close enough. If we're at pH 14, let's say, maybe even a little higher since it's not aqueous, and methanol has a pKa of, what, 18 or something like that, we're well within that 7 to 8 pKa unit limit. But then remember, even though this is identical to the final structure we're going to get, we've still got that acidic proton, and you cannot prevent it from being abstracted. You have to account for it. Remember what it means when we have a 2-step process, that we first treat it with base, and then when it's done reacting, we add the dilute acid. It means that everything's going to happen that can happen while it's in base, and only then will it stop reacting. So it's this enolate that's going to be dissolved in solution in the alkaline solution. And only then, after we add the dilute aqueous acid, well, of course, the first thing the dilute acid is going to do is neutralize any remaining methoxide ions and convert them to methanol molecules. And then as we continue to add the acid carefully, we will start protonating our enolate, and we'll get our final ketoester. And as long as we're careful with the acid, we won't hydrolyze the ester. It's certainly possible to isolate compounds like that, as long as you're careful and treat them with respect. Good, but that's an example of an intramolecular reaction. But I don't want you to think of either of these, either the mixed one or the intramolecular one. I don't want you to think of these as other things that you have to know. They're just other examples of the same thing. They're just variants on Claisen condensations. And we'll have a couple others like that today as well. But I wanted to be sure that we went over all that. Good. Let me just make sure. Good. Any questions on Claisen and Claisen knockoffs, spin-offs? And of course, if you think of a question in 5 minutes, that's fine. I don't ever want to imply you must think of your question within 10 seconds or else shut up. That's not how I work. Although for a goodly chunk of my career, people thought that was how I was, I really don't understand it. But that's neither here nor there. Good, so another thing that we've covered in the past, so it bears repeating, is conjugate additions. Oh, you have a question? Go right ahead then. Just sort of set this up. I'm just going to pull up the appropriate window. There we go. And your question would be, you can either unmute yourself or type it in chat. Oh, basically you only stop reacting when the enolate that forms doesn't have any acidic protons left. Well, yeah, well, once you form the enolate, then you're not going to deprotonate again because it's already got a minus charge. And like I said, I wouldn't be shocked if Owl is evil enough to come up with a case. But you want to look, once you've formed your product molecule, are there any protons alpha to a carbonyl anywhere? If so, they're going to get abstracted, and you can't prevent it. You need to acidify to make sure that you, carefully, if you've got ester groups, to make sure that you can isolate your product. And again, I would have to really sit down and think about it to try to come up with an example where all of the acidic protons are gone. It can probably be done. I've never really thought about it. But you need to look for them. See if there are any protons left that are next to a carbonyl. If there are, one of them is going to get abstracted. And so you'll need to acidify. And frankly, even if there aren't any, you will still want to acidify at least to neutralize the base, the alkoxide base, because otherwise you're going to have difficulty isolating your compound. You want to make sure that you get the pH as close to 7, as you reasonably can. That's also just best practice. So I think even if there aren't any acidic protons left, you would still want to neutralize the base. But you do need to look and make sure there are none. And I think in general you'll find there are. There's going to be at least one somewhere. We certainly had that on the last one. I think we're going to see that in this reaction too. So I would say the best answer I can give to your question is you need to be careful and look around for them. It's not something, and I'm not saying you're implying this, it's not something that you'll have memorized beforehand. It's situational, like so many other things in organic chemistry. Every situation is different, and you have to look for those acidic protons and make sure that if there are any and you're in alkaline solution, you account for them getting deprotonated since it can't be prevented. Good. Hopefully that answered your question, but of course, if you want to ask a follow-up, that's fine. Good. So, as I said, we've covered Michael or conjugate additions back in chapter 19. So if you've forgotten them, please review them in that chapter. What we said back then was there are certain nucleophiles that, given a choice of adding either directly to a carbonyl group or to the beta position of an alpha beta unsaturated carbonyl compound, will prefer to add to the beta carbon. And we gave a bunch of examples. Cyanide is like that. Cuprates are like that. Water is like that. What about amines? What about alcohols? Ammonia. And enolates are like that. And that's all fine, except at the time, we didn't really know what an enolate was exactly, except maybe by rumor. But now we do know what an enolate is. So this is a reaction we've already covered in chapter 19. But I wanted to make sure to show you an example that involves an enolate adding in a Michael fashion. So if you were to take this compound that's now dimethylmalonate and form the enolate by treating it with methoxide, and then you also had an alpha beta unsaturated carbonyl compound like this one, followed again by careful dilute acid workup, then you would get a compound of this type at the end. So I wanted to lead you through that mechanism, but I've already got the structures written down from the previous class. So, okay, so first step, of course, we're going to form our enolate again. And there's at least 3 good resonance forms that you could use, though 2 of them are equivalent. It's just a question of which of the ester carbonyls you use. Or you could put the minus charge in carbon, whichever you like. Maybe if I used that resonance form more often, I wouldn't keep making that mistake where I use the oxygen as the nucleophile instead of the carbon. But once you form that enolate, of course, you're going to form your new carbon-carbon bond between those 2 carbons. I just made up this dotted circle thing just now. I'm really liking it, if I do say so myself. So that's the 2 carbons you're going to form the bond between. And your intermediate will look like this. I have here made the new bond in blue. And then you do get an enolate. I think that one will be relatively quickly protonated because, as you'll see, we'll have an even better enolate to form, which is that this proton is very much more acidic than any of these 4 that are next to the carbonyl. Why? Because this one is between 2 carbonyls. So that's probably winning by a good 6, 7, 8 pKa units in terms of acidity. So I think it's actually going to be this enolate. Which do you mean the deprotonation? We deprotonate to form this enolate, and then the enolate adds to the carbonyl. I've indicated which are the 2 carbons that you're going to form the bond between. I think my arrows show that adequately, but it just makes it a little bit clearer. This is now the bond you formed. And here we're going to start by protonating this enolate because that enolate's not particularly stabilized. There's another enolate that we'll get that's very much better stabilized. So I don't think it's actually this enolate that we're going to get in the final mixture. I think it's actually going to be an even more stable one. Once we've put that proton back on, then I will argue, and quite successfully I think, this proton is way more acidic than either of those 4. And I think the difference will be quite dramatic. I think it'll be at least 6 pKa units difference, if I had to guess. So I think we're going to pull off that proton while we're still in base. And I think this is the enolate that's going to be present in solution. So this is the kind of analysis that I'm going to expect you guys to do. When you're answering mechanism questions, I don't want you copying from your notes or just going by rote memory. You need to be thinking about the structures that you draw. Where's my acidic proton? Well, that one's sort of acidic, but this one's even more acidic. So that's the way that's sort of the internal conversation you need to have. I am fully in favor of your talking to yourselves. You can especially talk to yourselves during exams now, since you're alone and no one will care. Anyway, once all of the molecules have gone to form this enolate, then we acidify. We add our dilute aqueous acid. The first thing the aqueous acid is going to do is kill off all the remaining methoxide ion and convert it to methanol, and then we will start protonating this enolate. And I think then you would be able to isolate the structure. Now, additional question. What if we weren't careful with the acid? What if, even at this point, we fully acidified and then heated up the reaction mixture? I would put it to you that this is the compound that you would get. So see if you can come up with the mechanism of that reaction. But I'll let you know that's a chapter 22 reaction. There we talked about the acetoacetic ester synthesis, and really the acetoacetic and malonic ester syntheses. This is actually a malonic ester synthesis in a way. It's just that instead of using an alkyl halide as our electrophile, we used this alpha beta unsaturated ketone. But it's no different. It's the same thing as what we discussed back in chapter 22. So there you'll review that if you wanted to, at the end of such a reaction, you could treat then with strong aqueous acid and usually heat it as well, and you will hydrolyze both esters, first one, then the other, and then you will decarboxylate. And I would propose to you that this is the molecule you will get out at the end. So that would not be a bad thing for you guys to review, for nothing else than for studying for the final. If we have time at the end, we'll go over that mechanism too. But I want to at least pose that problem to you. It would be one that is not a waste of your time to consider. So I'll leave that structure. I need to move chat, so I'll cover up that structure, but not that one. Good, so much for micro reactions. I have basically 2 more ideas to cover. I'd rather do the Stork enamine reaction second, is that it's a part of No, this is an additional step. Here I'm asking, what if you then treated with concentrated acid? Yeah, no, you're fine. I just wanted to clarify that. If you were careful, then I think you'd be able to isolate this compound. And I'm asking, what if we're not so careful? What if we dump her in, you know? So think about that. See if you can come up with that mechanism. I've already pretty much told you what would happen, and it's a chapter 22 reaction. And again, if we have time, I'll go over that, but I want to be sure to cover the Stork-enamine reaction and the so-called Robinson annulation first, since they're in the chapter. I'd rather do the Stork-enamine reaction second, since the Robinson annulation is much more relevant to what we just did. And honestly, this is another one of those name reactions, just like the Dieckmann condensation is the name for an intramolecular Claisen condensation. I don't really care if you know that. Mr. Dieckmann might, but he's not here to defend himself. Likewise, I don't really care if you know this is called a Robinson annulation. By the way, annulation is a $60 word meaning forming a ring. So, and I don't really care if you know that it's called that. Mr. Robinson might, but same thing, he's not here to defend himself. So, but it's simply, I mean, it looks dreadful, but it really isn't when you take it apart. I think you'll find that this is just a combination of 2 or 3 ideas from this chapter in a unique way. But other than that, it's not a new reaction. It's just an example of other things we've already learned from this chapter. So in a typical example, we'll start with a compound like this one. And again, we've now got a particularly acidic proton. And by the way, as I go through it, I'm going to be analyzing the structures as I go so that you can see what I mean by how to talk to yourself about the structures. But that proton's particularly acidic because it's between 2 ketone carbonyls. And now we don't have to worry about hydrolyzing esters because both of our starting materials are ketones. Those can't be hydrolyzed. So we don't have to use ethoxide as a base, but it's a perfectly good choice, nothing wrong with it. But there are plenty of other strong bases that we could have used also. And so we pull off that proton, we get the enolate, and then we make sure that we have this, this species present. Methylvinyl ketone is a very good Michael acceptor, and we just said that enolates like to add in a Michael fashion, like to add to the beta carbon of an alpha-beta unsaturated system. If there were no carbon-carbon double bond, then it would have the option of just adding to the carbonyl. But since it's got both options, enolates will choose to add to the beta carbon as though they have, you know, free will. But you know what I mean. They would prefer to add to the beta carbon. You'll get this intermediate here, and there's not too much that can happen here. So this enolate will simply get protonated by the solvent, but then we've got an opportunity if the base pulls off the other ketone alpha proton over here on the methyl group. Why? Because once it does that, now you're set up to form a 6-membered ring through a 6-member transition state. The reason that doesn't happen with this one is you wouldn't get a 6-membered ring, you'd get a 4-membered ring, and that's not going to happen. 4-member transition states are extremely unfavorable. I think I can count on one hand, maybe even on one finger, the Wittig reaction, cases where we've seen 4-member transition states. And that's only because oxygen and phosphorus like each other that much that they'll even go through a 4-member transition state in order to form a bond. But here, carbon doesn't like itself that much. So be that as it may, once we pull off this proton, now, again, I encourage you to number your protons. I do the same, but you'll form a 6-membered ring. Here I've made the new bond that we formed in blue, so you can see how we formed our 6-membered ring. And now we get to review about aldol reactions. And this really is more of an aldol reaction. But now when we, now this carbon doesn't have a leaving group on it, but if we protonate it, we should be able to dehydrate. And that's going to be, once again, by our E1CV mechanism that we learned about earlier in the chapter. So we'll form our enolate. And again, if you wanted to show the resonance form that has the minus charge in carbon, go for it. You're the boss of your sauce. However you choose to draw that resonance form, The second step of the E1CB reaction involves loss of hydroxide, and as you can see, we've effectively lost the elements of water, H plus and OH minus. And then we've got our double bond over here that's not only conjugated to this carbonyl, but also is tri-substituted. The only other thing I'm just going on in terms of analyzing the structure, asking myself, are we really done? Well, there's really only two other places we could potentially think of putting this double bond. One of them is over here, but in so doing, that double bond isn't conjugated to anything. So there's no reason that would form, at least no reason it would stay that way. It would migrate over here. It would be nice if we could put the double bond over here, because then the double bond would be tetrasubstituted. And it also wouldn't be exocyclic to the 5-membered ring. It would be endocyclic to both rings. But we got a methyl group here. And I'll bet you anything the authors put that there on purpose. That prevents that from happening. Because if you try to put a double bond there, you'll see you'll have a carbon with 5 bonds. So this, I would say, is the only product that we're going to isolate. I don't see the possibility of getting anything else. Thanks, Ashley. You're good to go then. So in any case, yeah, so that's the product that we'll isolate. But this is not really a new reaction. And I don't really care if you know that it's called a Robinson annulation. It's just another application of the material that we've learned in this chapter. Period, full stop. Good, so I would like to end with then the Stork-enamine reaction. And that will then be it for this chapter. And I hear tell from your colleagues, if you will, that are in the previous section to yours, I hear tell that Owl is particularly nasty about the Stork-enamine reaction. So I want to make sure we at least spend a good 5 minutes on it, even though it too is just another application of stuff we already know. We just haven't seen it put together in this way. And enamines we talked about in chapter 19. So if you've forgotten what they are or how they're formed, please do review that in section 19.8. And if you look at the structure of a typical enamine like this one, you'll see it looks kind of like an enol or an enolate. And indeed, they have pretty much the same reactivity. They're like enolates, they're excellent Michael donors. They like to add to the beta carbon of an alpha beta unsaturated carbonyl compound. So this particular enamine you would make by reacting cyclohexanone with pyrrolidine. Pyrrolidine is this cyclic secondary amine. It's basically like cyclopentane, except you replace one of the CH2s with NH. That's pyrrolidine. And so, so that's how you would make that one. If you then treated this enamine with, say, methylvinyl ketone, though there's scads of other Michael acceptors, I don't think the solvent really matters a whole lot. Ethanol would work fine. Then what you will wind up with is at first this intermediate. It's a little bit unusual. We've got a minus charge and a plus charge in the same molecule, or in the same species. I think we can rationalize that. We're pretty near pH 7. I don't see any strong acids or bases mentioned. That being said, we can now protonate our enolate and go back to the keto form. And so what you'll wind up with is this iminium species. And that we will then, in the second step, treat with maybe even, pretty dilute acid, but we would probably want to heat it to make sure that we can drive the iminium formation backwards, and you'll wind up reforming the carbonyl. And in the past, I had just pointed out that in section 19, it goes over that mechanism, and this is the very same mechanism, just run in reverse. But I got so many questions because A&M students ask so many good questions. I got so many questions over the years I've been here that I buckled and put the mechanism in your class notes. So I've already given it here for you. But the first step is for water to attack that carbon-nitrogen double bond. I think you'll agree that looks very much like a carbonyl. In fact, it's even kind of like a protonated carbonyl oxygen because the nitrogen already is a plus charge. And then, as is so often the case with these, we'll need to do some proton transfers. We're well used to that by now in acidic solution. We need to take a proton off of the oxygen because that's going to be our carbonyl eventually. We need to get the protons off. And we also need to put a proton onto this nitrogen since we want to lose pyrrolidine as a leaving group. So now we can do that. We'll form our carbon-oxygen double bond then, and water now pulls off that proton. Since water is what we're given, we're in aqueous acid, and I'm confident that that's the product that we would isolate at the end. So with that, I'm actually basically out of time, but congratulations, you are done with what I'd like to call the traditional organic chemistry material. And we just have a bit of spectroscopy to do. We've got some biochemistry to do from the perspective of an organic chemist. And then we'll do our polymers. And then I think we'll be done.